Let's talk about Lab 10. In this lab, you'll have a lot of freedom to design your project, your lab, however you want to do it. You only have just a little bit of instruction as to what you have to do. So if you read your lab description here, it says that you are to make a sequence detector. And the way this sequence detector is supposed to work is for every 4 bits, for the first 3 bits, it should output a 0. And then on the 4th bit, it should output a 1 if you have one of the following 3 sequences. So these 3 that are right here. And then there's a little example down here, and you notice that unlike some of the problems that you've had to do in class, it doesn't wrap around. Every 4 bits it starts over. So the first 4 bits are 1, 1, 1, 1. 1, 1, 1, 1, yep. And then, so the first 3, the output is 0. So the input is V, and the output is G. And so for the first 3, the output G is 0, and then on the last one, because it does match the sequence, the output is 1. Then you start over again, and you have 1, 0, 0, 0, and that does not match any of those, so the 4th bit output is still 0. 0, 1, 0, 0, again, does not match them, so zeros for all the outputs. 0, 1, 1, 1 does not match. But then 1, 0, 1, 0 is one of the sequences, and so on the 4th bit you get the output of 1. So that's how it works. So what does it mean, input or output? That's up to you to decide. What you have to do for your Prelab is to construct a state diagram and then to reduce it. So that's your Prelab, so that's to practice your state reduction. And then when you get to lab, you're going to decide how you're going to implement it. Well, you should decide before you get to lab how to implement it. And in another video, we'll look at some ideas on that. But first, let's talk about what you need to do for your Prelab. So I'm not going to do your exact sequences. Let's say that instead, instead of the sequences that you have to do, let's see how it would work for 0, 0, 0, 0, 0, 1, 1, 1, and 0, 1, 1, 0. Okay, so let's say that these are the sequences that we are supposed to detect. Just these 3. So we'll start by doing a state diagram and say that we start with some sort of reset. And then from the reset, now this is mealy because it's supposed to output, you're supposed to get the output on the 4th bit of the sequence. So our first step toward getting a sequence would be having just a 0 or just a 1. And in both of those cases, our output would be 0 because we certainly don't have our 4-bit sequence yet. And you might notice at this point that our output is going to be 0 everywhere on the right-hand branch of this tree. So I'm going to put what we're trying to detect over here so I have them handy. Okay, so then our next bit could be either a 0 or a 1. I may do zeros to the left and ones to the right. So this was input 0, output 0, input 1, output 0, input 0, output 0, input 1, output 0. So still, output has to be 0 because we don't have 4 bits. Okay, now let's get to our third bit. Okay, again, our output is going to be 0 on all of these. And I did 0 to the left and 1 to the right. So it'll be 0, 0, and 1, 0. Okay, so now's where the fun stuff happens. So what happens on my fourth bit? Well, it's supposed to start over after the fourth bit. And if I start with 0, 0, 0, 0, then if my fourth bit is a 0, then I have matched the sequence, and so I should have an output of 1. On the other hand, if I have an input of 1, then the sequence I would have would be 0, 0, 0, 1. Let me just put that corresponds to 0, 0, 0, 0. If I get a 1, that corresponds to 0, 0, 0, 1, which is not one of my sequences. So I'd have an output of 1. Okay, 0, 0, 1, none of that. There's no way to get an output of 1 here. So this is, I get an input of 0, I get an output of 0, and input of 1 also gives me an output of 0. Okay, 0, 1, 0. Does that match the first 3 bits? Nope. So this next one is also, whoa, 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 whoa. I did this going to the wrong place. We need to go to the reset because we have to start over, so not to the 0. So I'm just putting don't care 0 because it doesn't matter what I get from it. And then from 0, 1, 1, I see 0, 1, 1. It actually doesn't matter if I get a 1 or a 0. I will have an output of 1 from both of these. So this is a don't care 1. And then now I've matched all 3 of my sequences, so it has to be for everything here on out. Everything from here on out has to have an output of 0. It's not a very good state diagram, but there we go. Okay, so now let's make a state table out of this. I will call these states A, B, C, D, E, F, G, H, I, J, K, L, M, And I'm going to skip O because it looks like a 0 and do P. Okay, so now we'll put in the state table. Okay, so let's see. We've got the states through P. That was very close. Okay, and then from state A, that was our reset state. We will have that if, let's get all this. Okay, so not all of my lines got captured. Sorry, should have paused it. Yeah, so I moved my state diagram and somehow or another OneNote managed to capture everything except for the one little circle around that state. State I, whatever. Okay, so from the state 0 from the reset, if I get a 0, I go to state B. And if I get a 1, I go to state C. And then let's just work with B. From B, if I get a 0, I go to D. And a 1 takes me to E. And from D, I go to H and I. And from E, I go to J and K. And from H, I, J, K, L, M, N, P, from all of those, I will go to A. And while I'm here, why don't I just put the ones that have an output of 1. Okay, let's look at our output. We see that only H and K have outputs of 1. H has an output of 1 when V is 0, and output of 0 when V is 1, and K has an output of 1 regardless of the input. And everything else has output of 0. And you'll notice that all of the states on this bottom row, H, I, J, K, L, M, N, P, from H down to P, they all have the next state is going to be the reset state, whether the input is 0 or 1, because the next input after this is going to get us to the 4th bit. So these all have the same 0 and 1 successors. And then to fill in the others, we just noticed from A, I went to B if my input was 0, and C if it was 1. From B, I went to D and E. From C, I went to F and G, D, H, and I, and from E, J, and K, from F, L, and M, and so forth. Okay, so now we want to partition this, and we do it first based on our output, and we notice that there are just 3 types of outputs. You can have 0, 0, or you can have 1, 0, which is the case for H, or you can have 1, 1. Those are the only 3 types of outputs that we have. And so we can divide based on those outputs. So our biggest group is the group that is all zeros, and that is everything except for H and K. And then H has the output of 1 if the input is 0, and 0 if the input is 1, and K has the output of 1 no matter what. Okay, so that's going to be our first partition. Now we'll break it up based on 0 successors. And so we know that H through P all have P. H through P all have A's as a 0 successor. So we already know that we can put them together. Okay, now let's look at A. So we see that A goes to B, it stays in that same set. B goes to D. C goes to F. Just looking at the 0 successors right here. But D goes to H. So A, B, and C are together, but not D. I'll put D by itself for right now, unless we find something else that goes to H. E goes to J, which right now is in the same group. We see that it's not later on. F goes to L, G goes to N, and then we're at I, which is already in a separate group. So I just already noticed, so I'm just going to do this kind of not quite legally, but I noticed that starting with E was going to J. That is going to be in a different group. So I'm going to put E, F, and G together. And because they are eventually going to be separated anyway. Alright, so now let's look at 1 successors. I see that for the 1 successors, looking at this column, A goes to C, but B goes to E, so they're going to be separated, and C goes to G. So B and C will stay together because they both go to E, F, G, but A will be separated. D is already a singleton. Now let's look at E, F, and G. E goes to I. No, E goes to K. Looking at the 1 successors. E goes to K. And F goes to M. And G goes to P. So E gets separated, but F and G stay together. I know that I, J, L, M, N, P all have the same 0 and 1 successors. So I am probably pretty close here. I know that because I know that I, J, L, M, N, P are all the same. I have a lot of singletons that are not going to change. Now I just need to see if B, C, and F, G remain together all the time. So let me look at B. So B has as its 0 successor D. And C has as its 0 successors F. So B and C do not in fact stay together. Now let's look at F and G. F has as its 0 successor L, and G has as its 0 successor N. So far so good. F has as its 1 successor M, and G has as its 1 successor P. So that's good. Okay, so F and G stay together, but B and C do not. Okay, so this gives us 1, 2, 3, 4, 5, 6, 7, 8, 9 states, down from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 states. So that's pretty good. So 6 fewer states. Let's take a look at what our state table would look like. Okay, so I'm going to keep A, B, C, D, E. I don't need both F and G. I don't need J, L, M, and P. Ah. Okay, now let's make sure I have the right names for things in here. A, B, C, B, D, E, C, F. Okay, I don't have a G anymore. G is the same as F. Let's see, does that make sense? C goes to, let's look at what C does. So C goes saying it doesn't matter if it goes to F or G. And that's true. Why would it not matter if it goes to F or G? Because no matter what, it's going to have one more step, and then it gets to the reset, and it'll never have an output of 0. So F and G really are the same. So we would expect that F and G would be the same, and we would expect that L, M, N, P would be the same, as they are all. But L, M, N, P is not only the same, they're not only the same as each other, but they're also the same as I and J, because I and J both always go to A and always have output of 0, 0. Okay, D goes to H or I, but no, I've got I, that's good. E goes to J, which is in this high, or K, and F goes to L, which we're now calling I, and M, which is also I, H, A. Okay, and you'll notice these last three all have the same 0 and 1 successors, but they have different outputs, and that's why they're in different groups. So basically, I is representing all of those states that immediately return to reset with an output of 0, 0. So that is the reduced state table.